Yeah.
And perhaps we will get to see the quite interesting intersection of music information retrieval and natural language processing that he has brought to the table here. Bryan is currently in the job market, he tells me, and looking forward to his transition to the next stage of his life. But, well, thank you.
Thanks. Okay, so, well, he already introduced me, and I'm assuming you can all read, so you know what I'm about to talk about. Let me talk a little bit about the kind of research I do, and this is the best way that I found to sum it up. So I take artificial intelligence techniques like Markov models, reinforcement learning, and natural language processing ideas, looking at language models and prosody, to make auditory user interfaces for things like singing, transcription, music information retrieval, following jazz performances, and doing better karaoke for the masses. And so this is really human-computer interaction stuff that I end up applying it to. And I am part of the Musen project. And the Musen project is a joint research project between the University of Michigan and Carnegie Mellon University. The first line there are a bunch of professors at the two universities who are involved. And the second line are some of the grad students involved in it. We do things like music information retrieval, song identification, singer identification. We also do automated music analysis, such as structural analysis of pieces, finding the A section, the B section, repeated sections, and harmonic analysis, what are the chord changes. And we also make musical interfaces for things like automated accompaniment. And of those things, I am involved in just over half. So that's me, and you can see which ones I'm involved in. This is the thing I'm going to be talking to you about today, song retrieval. And song retrieval falls under the broad category of music information retrieval, and we are not the only people doing that. Johns Hopkins, actually a guy who was a professor here who's just moved to McGill, was deeply involved in making Gamera, or maybe it's Gamera, I never really know the right pronunciation. And clearly I don't know the right capitalization either. I chose not to capitalize document for some reason. Okay, that's what happens here. Variations 2 is something big at Indiana University where they are looking at linked streaming multimedia so that when you do a text-based search, you will call up, say, a Mozart symphony and get the score and the audio, and they will be linked, and the audio will play and the pages will flip for you while you hear the music. They're also getting into content-based search, which involves some of the technology that I'm going to show you today, where we did a joint presentation at the last joint conference on digital libraries in Houston, where you sing, it finds the song, it brings up the score, it plays the score, and the whole 9 yards. The University of Waikato in New Zealand is doing some work similar to the work that I do, and they're doing text and melody search of folk songs. OMRAS is another one, and it is no longer based in UMass and King's College because, let's see, Jeremy Pickens, the guy at UMass, is following one of the guys at King's College to City University in London. So you can still find out stuff about them if you go to those universities, but they're moving. And Cubby Hum at Phillips is another query by humming system like what I do. Okay, so let's talk about a little more about what I do. I said it's an example of music information retrieval, and you could think of music information retrieval, at least as we do it, as an example of content-based multimedia search. And so what are my motivations here? Multimedia databases are big, and they're getting bigger. In fact, we're helping make one right now. This, I hear, will be stored somewhere and maybe eventually digitized and become part of the multimedia universe that will need to be searched. Music audio is the stuff that I'm interested in and work on. The iPod. One iPod, which is somewhat smaller than the thing that you see here, holds 10,000 songs. iTunes, the largest, most popular legal database area, or database distribution software of audio, has 500,000 songs. And of course, anybody who's played with stuff like Kazaa knows that there's quite a bit of other music out there on the internet. So what's the deal? people remember content. Now, I'm not saying they always remember content, but they often remember content. Usually when you think of a song, you don't first think of the name. You think of the melody or some of the lyrics or something about that song. That's why you want to hear it. But databases tend to be keyed on metadata, which is distinctly different than the content which people tend to remember. So I'm going to make that statement. We tend to remember things like lyrics, melody, rhythmic patterns. And the database is keyed by title, artist, label. Or if you're on Kazaa, they might try and obscure it a little bit because you don't want the RIAA catching you. So what do? If I want to find stuff in a database that is indexed by one thing, and I remember it by another thing, well, I try and make some way of indexing it by the thing that I remember. Abstract representations of the database content are what I try to develop. Things that get pulled, hopefully directly from the audio, to give me the lyrics, the melody, the harmony. I do the same for some kind of a sung query. And then I use probabilistic database search techniques to find the things in my database based on my query. And these techniques have been inspired by things like FASTA and BLAST in the gene sequencing world and various kinds of hidden Markov models, et cetera, used in speech. So what is the exact problem that I'm going to narrow this down to? The information request is something along the lines of, I want to find a rock song that goes, "We're Dr. Pepper's Dr. Heart Love Band." Do you know what song that was? This is something that if you've ever been a music librarian or worked as somebody in a record store, or these days a CD store, this happens to you fairly often. They walk in, they have some general idea, it might be rock music, they might remember that it's a male singer and that there were some clanging guitars, and they can sing some portion of it. Help me find it. And the thing that I'm going to focus on is finding the melodic line, the pitch and the rhythm. So there are a lot of reasons why I want to look at melody. For one, there's all sorts of people like everyone in the audience here who does a lot working with speech, with text matching, with speech recognition. So in one sense, you guys are already covering the other side of this. But for another thing, here's something from kissthisguy.com, which I encourage you to visit if you want to see some amusing mishearings of lyrics. These are actual things that people thought "She's Got a Ticket to Ride" was saying. And my personal favorite is "She's got a chicken to hide." And I do not know what accent you have to have so that "she's got to take a giraffe" sounds like "she's got a ticket to ride." But apparently, given that there were two distinct people who thought things fairly close to that, there is some accent out there, some speech group where these are similar. OK, so what about my system overview? I said that there was going to be some kind of a sung query. We're Dr. Pepper's Dr. Heart Love Band. This is transcribed, quantized, pitch tracked, segmented, et cetera, and so forth, until I get an abstract representation. Okay? And then I've got some kind of a similarity ranker, which is going to match it against themes in my database. And I am not going to directly match against the target audio. I'm going to match against an abstract representation of a single line, or a set of them. So here's an example here, Sgt. Pepper's Lonely Hearts Club Band. And it's actually represented in my database by multiple monophonic, that means single note at a time, themes. And for those of you who do any kind of sequence alignment work, consider this problem. What if I had some sort of magical black box which output the complete harmonized arrangement of Sgt. Pepper's Lonely Hearts Club Band? I would have something like 10 or 12 different tracks of music all happening at once. And I'm trying to align a single sequence against multiple sequences. And this is a problem. And it's a problem you don't have in gene sequencing. It's a problem you tend not to have in speech work. Usually, they just stay completely away from cocktail party situations. Yeah?
In gene sequence one, you often have the problem of multiple
My understanding is that they're looking at, I could be wrong because I'm an audio guy, not a, I mean, I've read the stuff on Blast and Fast and stuff. But my understanding is that the catch is that in music, what someone tends to do is you might have this situation. Dun, 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 dun. There's Sergeant Pepper's Lonely Hearts Club. Dun, 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 dun. And they're actually skipping between these concurrent sequences. And so I have this problem of trying to go, there's this combinatorial problem of all the different paths I might take through them. And I'm trying to avoid that problem. And this is what I guess I'm trying to say. I'm trying to avoid that problem by representing this by a smaller set of monophonic themes which I'm going to match against. So the sung query gets transcribed. The targets have somehow been transcribed into a set of monophonic things against which I can match. The similarity ranker ranks the similarity somehow, and I end up with a ranked list, and hopefully the thing that I get out is the desired target. Okay, some example queries. This is going to take about 30 seconds. I'm going to play 30 seconds of a song, and I'm going to, in your own head, play this game with me. This is part of the user study that I did to try and find out what exactly I should be looking at in the ways of, what should we be matching against with queries. So what I did was I played songs for people, entire songs, and then immediately upon hearing the song, they had to sing back or say back or whatever back. I said, in an audio way, tell me or sing to me or say to me the most salient features that you would use to get me to recognize the song, okay? And this is supposed to simulate the idea of where you've heard a song on the radio, you'd like to get it, you've just heard it, you can still hang on to some portion of it. Wouldn't it be great if I could sing it to a device and have the device recognize it? So this was just to see what kinds of things people would actually sing to such a device. So listen to this 30-second clip. They heard the entire song. You only need to hear this part. And think to yourself what you would use, and then hear what they did. One of the lesser-known Beatles songs. And in fact, no one of these respondents had heard this song before. That was pretty much my ideal target audience. This person never even thought about lyrics, and they mostly covered the melody.
Go with him, da 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 da. Go with him.
This is someone who might be better served by a text base or, English language speech recognition model.
And just one more thing. Blah, blah, blah. Go with him. Go with him.
I like the blah, blah, blah myself. So there's a lot of extraneous noise, coughs, laughter. The kinds of errors that I'm going to focus on dealing with in this talk are where they get the pitch intervals wrong, the rhythms wrong, different key, different tempo, or dropped and inserted notes. And that's plenty for me to deal with right there. Extraneous noise, coughs, and laughter. Yet another problem to be dealt with at a later date. OK, so I do transcription. And when I talk to the students, not a whole lot of people here appear to have used Pratt. I don't know if that's true. OK, so there's a Dutch researcher, Paul, I can't remember how to, Boersma, thank you, who wrote this software Pratt, which a lot of people in the linguistics world use for doing the notation of the annotation of their audio, and it does pitch tracking. And we basically stole. He produced a paper. It explained his pitch tracking algorithm. It's an autocorrelation-based method, and we implemented it, and it works great. So I'm so glad he released that paper. So what happens? So you take a Sun query. We're Dr. Pepper's love band. Every 20 milliseconds, it does its autocorrelation, estimates the pitch. And here I have transformed the pitch into MIDI key numbers. These correspond to keys on the piano. So you could think of this as the 48th key from the bottom of the piano, for example. Here's time. This is what I'm dealing with. And I want to do something with this that compares it to a note representation more like what you would see in a musical score. So this level of detail is a little too fine-grained. So the first thing I did was wrote a segmenter, something which, based on loudness variations and pitch excursion, decides where a new note has probably begun. And these lines here show you where note boundaries have been determined to occur by my segmenter. Once the segmenter has done its work, a quantizer comes in and takes a median or mean, depending on which way I've chosen to do it. This one, I think, is a median. And then takes that pitch and forces it to the nearest piano note. So now I've segmented, I've quantized in the pitch domain, and I'll talk to you later about quantizing in the rhythm domain. And I end up with this. Sometimes I have pitch quantization errors. If the median is here and it just happens to be just closer towards the center of the wrong bin, I force it to the wrong bin. Sometimes that happens. I can deal with that by my error models and account for some errors with the quantization that I'm going to. Is that a question? Are you using? Yeah.
It seems like this kind of thing would happen often if there was, say, a quarter step off of standard tuning. They might go blah, 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 and it comes out as blah, 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 blah. And I wonder why it's actually necessary to quantize at all. So I'm guessing, because this is what I might do as a first pass, that you're going to be showing us a noisy channel model, which shows us how what they sang is a distortion of the true song. And in that case, it seems to me you don't actually need to quantize. You can have a distortion model that predicts these blue dots directly instead of the red line.
You have hit upon an argument that I have been having with the people at Carnegie Mellon University. Yeah. They are on your side. Yeah. I am on the other side. And one of the things that I do to help fix this model is you can adaptively move your pitch centers where if they've picked a pitch, and this example does not do this, but you can pick a center and say that's going to be where your center is likely, and it sort of adaptively move this model around, and that takes care of a lot of the problem where you're offset by a quarter tone, for example.
That completely answers that question. But the more general question about why you need to quantize.
Why did I quantize? I quantized, well, I'll answer it when I get to talking about database speed.
That's fine, yeah, do it if you want.
Anyway, sometimes I have short glitch notes. This short glitch notes was actually my fault, the singer's fault, because I kind of went, we're Dr. Pepper. But you'll have to take my word that sometimes I create short glitch notes. And this is part of the argument against my segmenting and going into the note domain. Here's part of my argument towards doing it. What kind of encoding do I actually use? I use pitch interval and rhythm ratio. And I'm going to talk about how this is tempo and transposition invariant and simplifies my error modeling for one thing. This is one big reason that I do this, because I do an error model that's note-based, because this is the world that I come from. But pitch interval and rhythm ratio. So instead of taking this note and dealing with it as a note, I take pairs of notes, and you could sort of think of this as diphones if you want. It's not, but I'm thinking about my transitions between notes, right? I'm going up 2 half steps, and the second note is shorter. And so here I've quantized into the half-step domain, which is the way my musical scores are notated. And here I've quantized actually to a set of 5 rhythms, and not in this talk, but if you're interested, I can tell you why I quantized to 5. I quantized to rhythmic ratios. Is the second note shorter, much shorter, about equal, longer, or much longer than the first note? And part of the reason that I go the way I go is cultural now. This is a kind of representation that was used before we came along. In the 90s, in the early half of the 90s, people thought that they could take a lot of the variation problems that people have where they sing in a different octave and their rhythms vary wildly, and simply remove the problems with these kind of variations by representing notes as simple note names, A, B, C, D, E, F, G, and removing all reference to rhythm. So here we have 3 things that look like strings now, and one of them, it looks like the word caged. Now, is caged more similar to gedba or cgad? I don't know. But now, is this more similar to this or this? So, although I played them in the wrong order, target 2 here is the query played in a different key. If I use pitch interval representation, this makes the difference go away. This is transposition invariant. As long as their pitch contour is roughly correct, once I encode it as delta pitch or pitch interval, they look the same. And my search problem has gotten easier. One of the issues that I have with my rhythm encoding, one of the things that people had done previously is typically use a fixed frame encoding for rhythm. And those who are using Markov models, now you guys may have more advanced, smarter things that you do in the speech world. But those who are using Markov models did the following. Here's what is this? Auld Lang Syne. Should old acquaint. Da, 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 da. Da, 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 da. Now I've got same thing played at 2 different tempos. Let's say for a moment that we've got a Markov model, and I assume most of the people here can deal with graphical models. One way that you could have it handle both of these things with a fixed time frame encoding is to have each hidden state represent a fixed interval of time, and then introduce some alternate paths through. So I can go 1, 2, zip, 1, 2, zip, or take the long road, and I can encode either one. This is inflexible because if I happen to pick a tempo which is longer than anything I expected, slower than anything I expected, I'm ruined. Loops. One typical way they handle this is using looping. Now, this is a problem that that's a little more subtle. Why not use looping? If I have 2 performances of the same thing, which are at different tempos, or I should say tempi, the slower performance will be reported as less probable than the faster performance because it has a longer path through the model to get out. Why does that matter? I'm not trying to say how likely is the observation sequence given the model. What I'm really trying to say is how likely is the model given the observation sequence. And I don't want this problem, and although I use the forward algorithm to get that. And I don't want a situation to occur where if I'm slow and I sing it slowly, I get a low probability of this model. And when I sing it quickly, I get a high probability of this model. I want it to be the same. So I ended up with explicit representation of these rhythm intervals as part of the state. G was shorter than the note that follows it. C is longer than the note that follows it. B is shorter, C is longer. And by incorporating the rhythm ratio into the state model, or the description of the state, I can model it more directly. And I don't have to waste lots of extra connections on handling rhythm time, or rather on handling tempo variation. my alternate pass through the model can be used for handling things like skipped notes and skipping whole sections. So what have I gained by this? I have a less complex model that seems to work better for me. OK. So that's part of the answer to the let me go ahead and answer your question now, actually, about that. So your question was, why don't I just use the initial representation as I get it? Every 20 milliseconds, I have a pitch track, et cetera. So the Carnegie Mellon people are doing that. And the way they deal with tempo and pitch tempo variation and key variation, pitch variation, is they actually do either dynamic time warping or they transpose, move the whole set of observations up and down in the frequency domain over and over again and do their matching again. And they have much longer sequences. So the sequence, this sequence right here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements. I've got 9 seconds times, what did I say, 50 times a second? It's a lot more elements. The sequences are much longer. And when I'm searching a large database, if I'm measuring a much longer sequence that has to be transposed in a number of different ways, dynamic time warping and moving up and down in the pitch domain, it takes, right now, their system isn't on the order of, it's 2 orders of magnitude slower than mine because of all this extra work they're having to do. And when you're starting to look at a database of 500,000 songs, it really matters that you're 2 orders of magnitude slower.
Sure, of course, there's a reasonable compromise in that you might use your system to get back the top 20 candidates, and then use their system to figure out which is the best candidate.
If they had statistically provable better performance, I would say yes, we should do that. But so far, we don't have that. OK. But we have a paper coming out about that you can read. Themes. I said that themes are the way I represent targets. So I've got some sort of audio here, which I then, you know the Sgt. Pepper's sound now. This is one of the themes that it is represented by. OK, I'm just stopping it because it rambles on. So the audio is indexed by themes encoded as MIDI. MIDI is to music as ASCII is to text. OK? So you record durations and which key on the piano got hit. And that is the encoding. Now, of course, I'm going to do some stuff with that later to turn it into this pitch and rhythm interval representation to make them the same as my query encoding. How do I get them? These are extracted automatically from the MIDI files. How do I get the MIDI files? Those of you who are into speech or music processing know that there are people like Bregman at McGill and a number of others, and several at my own university, who have been trying to do the stream separation problem, the identifying an unknown number of distinct sources in audio and separating them out. And you know that it's really hard, and no one's successfully done it. So how do I get the audio out? Well, luckily, there are these amazing streaming devices known as people. And apparently, these people have nothing better to do with their time than to take thousands and thousands of pop songs, classical music, not so much jazz, Christmas songs, and they sit down and they make MIDI files out of them. They make whole arrangements. They make them available on the internet, and you can spider crawl, grab them, index them, match them against your audio, and then we wrote some software to yank themes out of these. Okay? So we're sort of bootstrapping off of all the hard work that people have done out there already. I don't really understand why. I prefer listening to the audio myself, but they do it, so that's great. Moving towards extraction from audio, I've done some work to find harmonies directly from the audio because I believe that looking at the whole thing as a gestalt and telling that I'm in C major is significantly easier than saying how many different sources I've got. And Jeremy Pickens at UMass has sort of picked up on some stuff I did there with that and has shown that you can actually match on the harmonies and do some music information retrieval on that. Another guy in my lab, Mark Barch, has done some really good work on isolating singers in a classical music setting. And so we can also, in a classical singer accompanied by things like piano, pull out the singer and get the melody that way. OK, here's a little more of the answer to your question and more about the speed. Motivations for using themes, speed and relevance. Themes are around 50 notes, and even if I get this pre-made MIDI file for me, pieces are about 5,000 notes. And my similarity ranker I mentioned requires monophonic input. The obvious risks are coverage gaps. If my theme finder finds the wrong thing as a theme, something that you're not likely to sing, then I lose because it won't be covered in the database and it won't find it when you sing it. Themes are MIDI. They get turned into pitch and interval rhythms, or pitch and rhythm intervals, I mean to say, exactly the same way the queries do. And when I use a string matcher, it looks something like this. I get just a simple sequence. And when I use a Markov model, the theme gets turned into something with, there's the straight path through, and then there would be, now these are sort of random loop backs that I'm showing you, but you can imagine a situation where there's a chorus that gets repeated, or a verse that may or may not happen a couple of times, and you can put a loop in there. And I actually also have skipping models happening. And we've tried a variety. There's an infinite number of, actually not an infinite number, but a large but finite number of different connection models that you can try, and we're not nearly done exploring that space. I mentioned much longer, equal, longer, shorter. That's the kind of quantization I'm using for rhythm. So OK, how do I model the error? I do user studies. I play some kind of stimulus. I have the user sing back. Dun, dun. That's real data. And then my segmenter, quantizer, pitch tracker unit. So I treat the singer, pitch tracker, segmenter, and quantizer as a black input-output box. And that is the unit whose error I'm measuring. So as long as I train it on a particular singer with the same setup, I can use this model to account for different kinds of errors. 50 stimulus response pairs is the way I've been doing it for a particular musical interval. This 9 means it's an ascending interval of 9 half steps, which is also known to musicians as an ascending major sixth. I did, for this particular person, all intervals from an ascending octave down to a descending octave. Just so you can hear it again, here's another example. Dun, dun. As you can see, the segmenter and pitch tracker quantizer has some decisions to make about where that note really begins and ends and what the average is. So when you look at some of these errors, they're not always necessarily just the singer. But in this case, after 50 presentations of the stimulus, variants on the stimulus you just heard, I get a variety of outputs from my combined unit, anywhere from the exact right thing, which is the darkest, which means that it's the most often, that it occurred most often, and that's good, to a tritone, a major seventh. Generally, you can see a diagonal straight down here, which means that overall, the singer sings what he hears, but there's a little bit of fuzziness and error in there. Won't talk about that. You can play the same kind of game with duration. In a paper I can point you to if you're interested. I'll tell you why I ended up settling on 5 durational things. And this is actually a synthetic distribution that I use for anybody. This durational model is the same kind of thing. If 2 things were of equal length, someone is most likely to sing that, a little less likely to sing the second one shorter, and very unlikely to sing the second one much shorter. This is an exponential decay model off of the diagonal that I put together after observing a bunch of people, and it's sort of a part of my steps towards making this thing singer independent. Okay, I used two different kinds of matchers, of similarity rankers, to talk about the similarity between my sequence that gets sung and the sequences in the database. So if I've got a target, which is something in my database that looks like caged, and I've got a query that looks like this other thing, it gets transcribed somehow, the cost of calling this interval a match with that interval is determined by the error model that I collected. And I say that the more often that this occurred, the less that transformation will cost me. So that means that if I know someone is likely to sing a tritone when they really mean an ascending major sixth, I will say that when I see that, transforming my query into my target in that way is a relatively inexpensive operation. It's something that happens all the time. So I use a probabilistic string matcher to do this, which is extremely similar to what is used in gene sequencing. It takes order n times m time, where n is the length of the query and m is the length of the target. And the basic operations I've got going for me are skip an element of one or the other, or call them a match. And the error model, I already said this, gives how much I'm going to reward a match. Another way of doing the same thing is to have a hidden Markov model. And these Markov models are constructed in a way that is perhaps atypical. The model itself is built off of one of these modified themes automatically. Then there's going to be some sort of connection model that we use that has something to do with the way we think people are likely to skip around in the piece. This is going to be combined with, again, that same Singer error model. And this is going to be my observation probability distribution that I use now. And I will use it to run the forward algorithm on the model and find the probability of generating this query given this target. I run the forward model, or the forward algorithm, on all the models, and the one that seemed most likely to generate the target is deemed the one that is the best match. And this kind of constrains the way I make them. I have to have them all use the same observation probability distributions, and my hidden states have to have the sort of same meaning for it to be a meaningful comparison. The reason a Markov model could potentially be better than a string matcher is if you can get the connectivity of your model designed properly, you could have a better model of the way people make their skips and repeats, and it might do better. The architecture can be arbitrarily complex, and that can cost you in time. OK, yeah?
Do you introduce additional states into the model besides, I mean,
Non-observable states, do you mean? Or?
No. So I'm thinking that case is where somebody just gets the note wrong. You're talking about skips and repeats. So you couldn't pick that up in the Singer error model.
If you mean,
another option, suppose there were two notes A, F, and I remembered that as a G or something like that.
Well, OK, now that would be in some of these cases, the error model could catch that.
The Singer error model.
The Singer error model could catch that.
So there's a difference between thinkos and typos, right? And
sure.
You might want to model those differently. So one is an error of memory, and the other is an error of production. You may have studied both. Your user study looks like it would be pretty interesting to try to distinguish those two kinds of errors.
I only studied production errors. That was designed only to handle production errors. Another guy who just got his PhD from Michigan has what you might call, or he might call, a more of a memory production model. And he made a very complicated Markov model and wrote a whole dissertation on all the different ways that people could mess up. And if you're really interested in how the most sophisticated way I know of attacking it is, you'd have to read his dissertation, and I can point you to that.
Great, thank you.
So a working database. This is very small. Database people will laugh at the size of this database, but this particular database is the one that I'm currently working with. It's got 259 songs made by the Beatles, a bunch of cartoon theme songs, a bunch of jazz pieces, and well-known pieces like Waltzing Matilda. Before I get to this, I'm going to do you the demo. I'm going to show you some of what I've been talking about. Because I was going to start talking about some results of using this thing on people, but why not show you? This is a string matcher-based database searcher that's going to return a ranked list of targets based on a sum query that gets segmented and pitch tracked just the way I'm talking about. So I did this for the students earlier, and OK, for those of you who weren't here, I'm going to play the segmented query. Tell me if you know what song this is. Yeah, it was I Am the Walrus. Here's what I sang.
Oh, la-di-da-di-doo-di-da-di-da.
Oh.
Boo, 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 ba, ba.
I'm sorry, I re-recorded. We were testing something earlier. I'll tell you what. Why doesn't somebody give me the name of the Beatles song? You will. Oh, I don't know the song. You. Okay. Okay, I'll do Hey Jude because I do know that song. Huh? Oh, actually, where is I Will? Could you sing it?
Sure. That's, no words, I guess.
Yeah.
It's good because I don't remember the words.
This is going to be a real test because it was trained on me, but let's try it with you.
Yeah, should I come up?
Yeah. Okay, what I'm going to do, come over here because the mic's over here. I'm going to hit record query, and then it's going to go for 10 seconds and then stop.
Bum ba-dum 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 bum bum ba-ba-bum bum ba-dum bum ba-da-dum dum ba-dum bum.
All right. Now this is a little, let me just say I'm really taking a risk here because this one was modeled on my singing. So first thing it does, the first thing it did was pitch track, segment, and did all right. I Will came up second.
Yeah.
Let's see if it's in the.
Who knows how long I've loved you? You know I love you
Still. Oh, now I know which. You know, the funny thing is.
The reason that I picked that song is it was in my head for about 3 months before I figured out what it was.
Ah, well, you see this.
I really wanted your sister.
This could have really helped. So let me hear how the segmenter did on you. Found it anyway. Came up second. This is an example of what happens with the training, though, where my error model is compensating for some problems that my quantizing and segmenting has introduced as far as rhythm and some things. What I should do, actually, we'd have to listen to the whole song to know. I'll play the target. I'll play the. No. I'll play the target first of all, and so maybe you'll hear it. But I don't know where in this it is. So I'm not really sure. One of the things that you have to know is that things that sound similar to us, it's not always necessarily the same to the machine. You know what is similar and what isn't. But let me do this. This is, whoops. This is the distribution of scores of all elements in this Beatles database right now.
Against this query.
Against this query. And so I was going to zoom in on the top couple. So this is the right one. This is the one that came up first, unfortunately. But again, the plan for this is something where it gives you a Google-like answer. if I get it in the top 2, for example, it's reasonable that you're going to do what I did and, play the first one.
She's not a girl who miss,
No, that wasn't it. Hang on.
who knows how long I've loved.
Oh, yeah, she's not a girl who knows how long. It's got sort of a similar pitch contour anyway. That's kind of the point of this, is that it's helping you find it. It won't necessarily always get it right, and now we're going to get to how often it gets it right by getting back to the talk. Let's go to a performance evaluation.
Question, Bryan.
Yeah.
You try to weight regions of common themes of the chorus more heavily. Presumably people will remember the repeated elements perhaps more strongly than they will the introductions.
The way that tends to get weighted is by, this gets into the theme identifier, and there's a lot of stuff happening in the background in picking out the themes to begin with. And the hope is that it's picking out the choruses and things. There are highly repetitive elements. There are highly, such as Alberti bass, which due to their short nature and repetitive nature are going to get cast out. There's been a fair amount of work on trying to tune something to pull out what is a likely thing that a person would identify with. And we've had different arguments. I've been, in fact, arguing for more user studies on this. And one thing that I'm trying to incorporate now is I want to save off every query that I get and save those pitch-tracked queries as something that I can use for correcting the system. So that way I can introduce new themes that may be sort of a munged-together version of a number of queries if I can do that, which would help me get around this what people remember issue. This requires active user training of the system, though. You sing, and I've been doing some of that, and the fact is it's slow because it takes a lot of getting people into a lab and getting them to do my stuff. Well, here's a performance evaluation. 36 subjects were asked to sing a song as if you're trying to find the song using an online search system or kiosk. This resulted in 155 usable queries, and by usable, somebody like me sat down and listened to it and went, oh, I think I would recognize that. And the theme for it was actually in the database. So this is going to be something in a good world where some portion of what they sang is actually covered in my database. And this is using a database of 868 pieces, or roughly 9,000 themes. Oh.
When you say usable identified by you ask them if that's the song they have.
Yeah. So what happens is they sing it, sing the song, tell me what song you were singing, then have somebody else listen to it and go, I think that's song X. And if we all agree that this seems a reasonable representation of song X, that counts as a usable query. So we're talking, this is a nice world where people are singing recognizably and targets are in the database. Much nicer than the real world. And how well does it do? Well, this is one of the HMMs. This is actually one of the more complicated HMMs being represented here. This is something put together by Colin, who had that model of memory and all these other things. And the note interval thing is actually a note interval-based string matcher. And one of the things that you're going to notice from this, first of all, is we haven't found a real superior HMM architecture to do much better than a string matcher does anyway. Does a little bit better, but as you can see, it's not really a significant difference in this particular example, and that holds across other experiments. Gets them first about a quarter of the time, drops off like this. Now this database is 900 long, roughly, and it gets scattered randomly throughout the database, the errors. The errors between the Markov model and the note interval are somewhat correlated. R squared is like 0.5 or something. they're enough correlated that I'm not, that a large portion of these are because our models are not recognizing what this person is singing, as opposed to two different approaches having fundamentally different ways of seeing the world. So this is a small database. So one thing you could do is you could build a giant database and then do it again, which is something that, frankly, needs to get done. Another way of studying how well this would actually do in a larger database is sort of try and find out how the performance changes as database size changes. So here's the game. If you do all these queries, all 155 queries by the 36 singers on the big database, and you get some results down here that I already showed you. What happens if we take these queries again and make a new database which consists of only the right answers, the desired target? Well, clearly your performance would be 100% correct. Now we introduce a confuser. Now we've got a database of size 2. How well does it do then? Now introduce another confuser. Databases 3, 4, 5, 10, 100, 300, and so on. And if you repeat this, say 50 or 100 times for each database size, randomly picking from your original database a different set of confounders, you will start to see how the performance changes, at least on databases like this, given the size of the database. And so this was actually done, so you do this, we did it 50 times, for each size of the database, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, randomly picking confusers each time, and charting the performance, and the averages here are being displayed. Now this is mean reciprocal right rank, which has been turned into percentages. So 100 means it always gets the right answer first. 0 means that we're doing, well, 0 is actually, is it possible? 0 is impossible. Do any of you know what the trek is? So this is a numerical measure used in that world, and we're trying to make Trek-like things in our world. And how do we do? Well, the HMM is green, the note interval string matcher is red, and 1 over log n is the model that seems to best fit where n is the number of songs in the database, the performance. Now, it's actually a little better than 1 over log n, they both are. And whether these trends continue, we're going to move up to a database which is 10 times as big. It's a little labor intensive to double check all your themes and all your queries and everything else to see if this holds, but it provides a provocative prediction, and it makes a nice, easy thing to make my next paper about, right? I say, this is the hypothesis, and now let's test it, and that's coming. There were a number of different scaling models tried, and 1 over the log seemed to be the best. Let's talk about system speed. The complicated HMM with all the memory models and transposition models and all the other things took much, much longer than the string matcher. The string matcher used by Carnegie Mellon that went off of the original audio takes roughly as long as the HMM because it performs 144 different transformations of the data to try and deal with tempo and pitch, or tempo and pitch variance, key variance, that mine doesn't have to do. And so what we end up with is a situation where the string matcher is 100 times faster. And now on our database that we were working with, 2 seconds versus 0.2 of a second isn't a big deal. But if you move to, say, 900,000 songs, 20 seconds versus 30 minutes is a very big deal. And of course, this is on a Pentium 4, right? And yeah.
You told us that you had a string matching problem that was original, because there were one string in the query, we compare with several strings.
Yeah. No, I don't have a string matcher that is, quote, original, as in fundamentally mathematically distinct from the kinds that they're using in other fields. I have a workaround, a cheat, which is I treat the different channels as independent strings, and so I have a set of monophonic strings that I match against my query, and then I've got another target that's represented by a set of these things, and whichever target has a single string which matches best against the query gets called the best target. So I'm sidestepping the problem, and I do not, in fact, currently do what I was talking about, skipping between. That would be great, and if someone wants to give me a little research money and a position where I can spend time doing that, that's on my list of things to do in the future. Yeah.
So on the previous slide, you were,
Here?
I think, suggesting.
Here?
No,
Here?
Next one.
Wait, next one.
This
one.
Yeah, right, previous on the justification. I think you're suggesting that you have to run the string matcher or the HMM on every song in the database separately, one at a time, before you're willing to come up with an answer.
As opposed to having a structured database where I have exemplars or some way of immediately pruning.
There are lots of ways of doing pruning, yeah.
We're right now testing.
Or parallelism in the case of sharing.
Oh, yeah. Parallelism is an obvious thing to do here. But I was going to say that I'm measuring right now the performance of this as opposed to the performance of various kinds of pruning or other techniques. Wanted to see how fast I could make this before dealing with the other things. And in fact, there's a researcher, a database guy who's affiliated with our group, Jagadesh, Professor Jagadesh, who has been talking to me about a variety of things that could be tried, and I've been talking to one of his grad students about trying some of them. So this is being addressed, not directly by me at this time, because again, I'm working on the core matcher here and seeing how fast I can make that and how accurate I can make that. But if you have suggestions, I would love to hear them afterwards and lobby for them. Okay. Anyone remember the story of John Henry? This is the guy who, now, I've heard two different versions. One is he's driving railroad spikes in, and the other is he's digging. But it's basically man versus machine. And in the John Henry story, man wins. And it kills him. But in this case, it isn't, the stakes aren't quite so high. I wanted to compare how well someone could recognize these queries versus how well the machines recognize. How well can we expect to do? And now you don't necessarily want to say that human performance is the necessary upper limit, and there are going to be a number of ways you can rip holes in this next thing that I show you. But it's going to give you a good sort of ballpark estimate for how well people do. What's the task? Sing every Beatles song you know, given a red list of titles as a reminder. And I said up here, but what it really was everything you're confident of being able to sing, which is distinct. Don't use words. Present queries to the string matcher, one of the variants of the Markov model, and now this time the Markov model will be a simpler one, and the singers themselves 6 weeks later. And the singers actually have a couple of advantages in that I should have played them the segmented audio, but instead I played them their original source files. And they didn't have to name the tune correctly. They had to get any portion of the lyrics or any portion of the title other than a word like the. If they got that, they got credit for the right answer. So this is just some people in our lab, had them sing some. And so what are these numbers? Other two singers. This means that one person sings and the other two people 6 weeks later listen to their singing. Now these are all people who have been working on the same Beatles database, who know each other, who have heard each other sing. They're friends, and they have a pretty good idea of what each of us sounds like. 2 out of 3 times we could name it. The HMM and the string matcher, now we've seen the performance flipped, although again, it's not really all that statistically significant. These guys are getting it in the range of half right. Someone may point out, singer 3 has these high numbers. These singers have lower numbers, especially singer 1. When I ran this test, I made a mistake. I wanted to use my generalized singer model. I set something wrong. I used the singer model for myself. Okay? this, but I'm going to report this to you anyway because I think it's a little interesting. This is me. This is how well the string matcher and the HMM do on me when my singing model is the one used. This is how well they were doing on them. And again, you only get a point if you get number 1. Number 2 doesn't count. So 70% of the time on me, on the Beatles database, I can nail it number 1. And it's worse for the other 2 singers. This singer here, do you remember the one who went da, da? That's him. Very interesting, I thought, is this diagonal here just as the ultimate. This is the ultimate performance test. I can't imagine doing better than this. This is singer 1 singing, and then singer 1 6 weeks later listening to himself. Singer 2 listening to himself. 3, that's me listening to myself. This guy sucks, okay? He sings very badly, yet he's got a perfect model for his own error, and he can nail it. He knows what he's saying. He knows what he's saying better than I know what I sang. I have a master's degree in music. I had to take years of sight singing. I've listened to these. I don't know what to say. So this gives me hope that even a very poor singer, if you've got the right model and the right way of attacking the problem, you're going to be able to get really good results.
Singer 1 probably has a lower baseline performance. He doesn't know as many songs.
That may be. And so but I mean, this is him on himself. I just thought it was fascinating. 2 of us, these two, we both have graduate degrees in music. And we both clearly know the database that we sing from. And 6 weeks later, neither of us could, he did even worse. This is a cello player. I was just amazed that 1 out of 5 times he couldn't even recognize his own singing. OK, so this is getting towards the end now. What have I done? Well, I've got a useful working system that uses a couple of different matching algorithms to find your song when you sing it. We're developing, this isn't completely done. We've got a test bed now that we've been sharing with the people at Carnegie Mellon, and we're in talks with Stephen Downey at the University of Illinois, and we keep getting together at these joint conferences on digital libraries. We're trying to make a Trek-like evaluation system for query by humming so that we can truly compare methodologies against each other. We've got that going for ourselves and Carnegie Mellon and starting to get it going with Illinois. The problem right now is that everybody has different databases with different evaluation metrics, and it makes it impossible. People get together and it's that Macintosh versus Windows argument, or it's religious rather than based on fact. And we're working to eliminate that so that we can actually start to say, these approaches are better, these approaches are worse. These algorithms can be useful in related research. I also do research in speech prosody, and it's very clearly applicable to finding things like subject, part of speech, anything where you've got prosodic information that you want to pull out. This same technology can be used to match against, say, Toby-style, and this is something I want to do. I'm working on making an automated Toby-style annotator. Do you guys know what Toby is? OK. Gene sequencing. One thing I haven't talked about is how I deal with gap penalties. They are fairly uninterested in details of that, at least as far as I could tell in that research. We are more interested in gap penalties because we're more interested in rhythm and timing, and we've done some stuff in there that's useful to look at. My research agenda on this project, as opposed to other things that I do, metadata extraction from source audio. So I've talked a little bit about how I am approaching doing harmony extraction from audio, and there's a couple of things out on that. Generalized singer error models to eliminate individual training. This is a big deal because, as those of you who do speech work know, it's hard to get people sit down and spend hours reading text to you so that you've got a model of their speech. Multiple sequence alignment models. This is what you were hoping that I was going to talk about, apparently, and I don't have anything other than a brute force approach right now, which is try all my paths, and that's a stupid approach because it uses way too much time and slows me down too much. integration with other search engines. All I've talked about here is finding it against the melody, right? The rhythm and the pitch. But clearly, if you know some lyrics or if you know it was by the Beatles, you can narrow it greatly. And the combination of these things can find your answer. And I've already mentioned that we integrated some of this search technology into the Indiana University Variations 2 project. Already talked about Trek-like evaluation. If you are interested in stuff that I do stuff on this query by humming, which I've just talked about, automated harmonic analysis by computer. That means finding chords. It's not other kinds of harmonic analysis. Musical score following. I also do things for following jazz performances based on a jazz lead sheet to give you an accompanied performance. I mentioned speech prosody. This is where you can find the papers. Most all of them are available in PDF format on the web. I think, yeah, that's it. That's my talk. So, any questions? How much time have we got? What happens now?
We have -8 minutes.
Oh, I'm sorry. I'm sorry. I didn't mean to go over. Silence. Oh, wait. He hasn't asked a question.
I mean, it's a little far out, but I guess it's more on the modeling side, on the engineering side.
Uh-huh.
Are the sorts of big Markov models or other sorts of graphical models being built for music expected to model in some way the structure of music might perhaps a context-free or mildly context-sensitive models be interesting ways to attack modeling musical structure?
They are intended to model musical structure, or it depends. I personally have tried a number of variants. For my score following work, I am very interested in modeling musical structure and very interested in following it at multiple levels of abstraction, too. Whether it's the individual note level, the underlying harmonies level, or the level even of a much vaguer model which says, I think I'm in the bridge. And so connectivity at the micro level, skips and jumps between different elements, repeats that can happen there, and at a macro level and an even super macro level, I am interested in modeling, and we can talk about it. I haven't published that stuff. That's in my dissertation, and just as soon as I finish it, I'm going to turn around and start turning it into papers. So I will have stuff out on that, and I can even maybe send you a preprint if you're interested. Yes?
So this is going to be like sort of stupid baseline question, but people talk about how music sort of all sounds the same, like that rock bands produce, things that copy other ones. Is that going to be figuring, if you have lyrics, then obviously that'll help, I think, disambiguate it, but if you're just relying on melody or rhythm, is that going to be a problem as you get into more sort of generic genres, perhaps?
Well, that is an issue. Okay, so the issue here is how distinguishable are the different elements in my database given the representation that I've chosen to use. So for example, I think I showed you when I chose to represent things as character, like ASCII strings, caged. The distinguishability between my targets maybe is reduced. So the problem here is how do I hang on, well there's several issues. How do I make things distinguishable yet not introduce non-salient information that people are not going to pay attention to? So far, we've been pretty lucky. We've been using music which is very melodically based, right? There's different ways the distinguishability could go away. One thing that could happen is I could have a quote. Now if musician A is quoting musician B, clearly there are going to be passages that are indistinguishable, and that's on purpose. The other possibility is exactly what you're talking about. Yeah, all those blah, blah, blah bands sound the same. If, in fact, my representation and as the size of the database increases, you're going to have more and more confusers that are going to look more and more like your target. And how bad that's going to be is going to be a function of the style of music you use and the representation you use and the size of your database. So far, dealing with melodically oriented music, as opposed to, say, rap, and databases on the order of, we've tried with synthetic databases up to around 10,000, and we're still doing okay as far as this distinguishability goes. It could eventually be a problem, and what you're talking about would be the way we'd solve it. I also would ask you for who did it if you know, or if you can tell me that it's a 1970s band, and then I can use metadata to winnow down my database and hopefully have distinct elements again. That was a little long-winded, but I hope that answered.
Actually, I was just realizing that lyrics got your problem. You said, you know, blah, 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 I'm in love with you.
Ooh, baby, baby, yeah. Yeah.
A little bit different. Well, so basically what you seem to be doing on the low level is sort of a string comparison, right? So what your query is and what you're actually getting. And you're doing it based on the interval patterns.
Yep.
So going up and down. So two things on that, I guess. The first is using intervals versus notes. It seems like there's a couple extra penalties that you might be including that you don't need to have. So, for example, you had in your example going up a major six. So like dum dum. So if the singer was to perhaps go like dum dum dum, then you've added, by inserting something into that string, you've not only included an extra descending something, but now your other interval has changed. So you've lost the
That's true.
note. So you've inserted a note in the middle, you've lost that interval in between. You might not, well, so I'm curious as to whether or not you include that or consider that when you're doing your string comparisons.
Similar problem for rhythm.
Yeah.
And then the other question is, let's say instead of going up a sixth, you go up a seventh, and then you go back down a seventh versus, and so the original pattern says go up a sixth, go down a sixth. Instead you go up a seventh, go down a seventh. It seems to me that that should only have one penalty. I would look at that as one missed note, but then you go back down to the regular key,
Right.
etc. And that would be penalized more than if you actually went up a seventh and down a sixth and shifted what key you're in. So I wanted to know if you considered that at all in your scoring.
You have, okay, so there have been two little raging brush storms of argument in our research group. One has been this, why segment at all? Why don't we go straight off of the initial pitch track? And the other one is this, what you might want to call absolute versus relative encoding. The relative encoding has this issue that you've just described that I kind of introduced two errors. And yeah, why not do the absolute? Well, for one thing, it's, okay, when I did user studies of, now this is, again, based on just the two-note intervals, right? When I did user studies of the kind of pitch interval mistakes they made, and I looked at it in this relative encoding, how far off they went, just considering the interval, and then I looked at it with this absolute encoding. Here's one problem that I'm going to mention. Octaves. When the interval is too high, they're off by 12 half steps, which is a octave. Or when it's really too high, they're off by 2 octaves. And this was one thing that I observed. And this is for a particular speaker that I did this for. So on the one hand, I'm paying the penalty that you've described. I introduce two errors when they jump up to the wrong note, but then correct back and stay in the right key. There are other kinds of errors that get introduced by being in the absolute realm, one of which is octaves. And I really felt like, so this is one kind of thing that other kinds of errors are introduced. The other thing that happens is what I talked about with the absolute thing. How do they compensate for people singing in a different key? And the answer is they literally shift everything up, try it again, shift everything up, try again, and do this. So if you do that 12 times to go through all 12 keys just to make sure, your matcher is going to take 12 times as long. So now the question is, are you willing to pay the price of taking 12 times as long to solve your problem? I was arguing that speed was better. Roger Dannenberg argued that we'll get faster machines, so we're going to try all 12 transpositions. It's a trade-off.
False dichotomy. A speech person would try all 12 in parallel and put it up the ones that would poorly wrote speed.
Okay.
And there are video representations you can play with also. But
I mean, it seems like taking into account what Ryan was talking about, you look at distance from time, you find that, then you can
Ah. If you could find the tonic. Now you've just introduced a very important, we'll call it a linguistic structure now, right? The stuff that I've been talking about here didn't require me to have a deep literally part of speech kind of understanding of my string, okay? If I have to find the tonic,
Well, look, I mean, you could do it just say, okay, I'm going to take the first note and say, okay, that's what I'm going to look at all my relative references in the rest of the song and resolve to that note. So you look at the distance between that, and that would compensate for the kinds of problems Aaron's talking about. If you go up, you go down by the same distance, you're still where you started from.
there are a number of fun things you could do. One of the things that,
Histogram is the most common, right?
sorry?
Pitch histogram is the most common, right? So if you want to match against the, I mean, that's a typical way to keep it.
Yeah. Oh, that's what you mean. Yes. That is that's Karen Krumhansel. Where is she now? UCSD, I think. Did stuff like that to find the key. There are a number. We've also tried things like quantizing everything to all the different modes, like all the 12 major keys, quantizing it to all the minor keys, quantizing it various different ways. So this is a way of approaching it where by sort of brute forcing it into a bunch of different key representations, maybe you can force these errors out of it. What you're talking about is something that I think was proposed but never done by anyone in my group. But that's a great thing. You can actually take my paper, write a follow-up paper, and reference me. I think someone else had it.
Wouldn't that assume that the themes that you have found to build your database began at the same node as query, which isn't always necessarily true?
Well, when you say begin of the same
Take
note.
this approach of, well, let's say all themes start on C, and then we'll normalize the query to start on C.
Uh-huh.
The query and the theme don't necessarily start at the same place, right?
Right. And that's where you end up starting in all 12 possible keys to get around that. So yeah, this is great. I love these speech people questions. Anything else, or we about covered it?
Just one quick question.
Okay.
Do you match against, I've got lots of questions for all three. Do you match against the whole theme, or can you match against segments?
That's a really good question. So a thing I didn't show you that will be in an upcoming JSIST paper, Journal of the American Society of Information Technology, looked at global matching versus local matching. And local matching where I allow a restart anywhere within, basically the answer is I do allow matching only considering subparts. I compared it to forcing a match against the entire theme, and the average query is about 1/10 of the length of the average theme, and going to a local matching algorithm improved performance noticeably, and the one that I demoed just here was a local string matching probabilistic algorithm. So yeah, we looked at it, and global is worse.
And what happens if you have this person sing the query more than once?
In what sense?
We should probably, thank you.
Yeah, maybe we can end it and just talk a little more, the two of us then. Would that be? That sounds like it. Thanks.
Carnegie Mellon is actually where I did my undergrad.
Oh yeah? So you know Roger Danner?